Okay, so the title of my talk is Are Orbitals Real? And I wish to emphasize about what I mean by real. Real is a measurable quantity. And I would like to begin to say what is the motivation to this talk. Orbitals are used as building blocks, basic concepts in modern chemistry. When we teach or when we learned about the periodic table, we learn that hydrogen, for example, has one electron in the 1s orbital. And then we said in the periodic table that helium has 2 electrons in the ground state. The 2 of them occupied the 1s orbital of helium. When we look at the periodic table at lithium, we see the configuration 1s square, 2s, and etc. When we discussed in basic course in chemistry about molecules, we learned that H2O looks like this, has such a structure, while CO2 is linear. And the explanation in the basic course of a freshman chemist is that the H2O makes from hybridization of orbitals, and they speak about sp3, while CO2 is made from a hybridization of sp orbital of carbon. And this difference in the structure, what we know, is very, very important and basic, because this molecule, H2O, which has slightly negative charge here and positive charge on the 2 hydrogens. Let's mark it in red. The 2. This molecule has a dipole moment. There has a permanent dipole moment, while CO2 has a 0 dipole moment. And the fact that H2O has a dipole moment has a crucial role in the construction of life on our planet. And the reason that we are looking for water in order to establish life on the planet is because H2O has this structure and not like the CO2. When we look for life out of space, and we are looking for life which is similar to ours, we also again look for water. So the construction of H2O in this form, because of the orbital structures as we learn, is very important for essence of life. And then we ask ourselves what orbitals are. Is the orbital of 1s hydrogen is like the 1s of helium? Of course not. How they are defined? And this is one of the problems of teaching basic chemistry. Because the concept of orbital, which is a basic concept in chemistry, results from advanced concepts in quantum mechanics. In a recent book that was published in Hebrew on quantum mechanics from foundations to applications, the first time that the concept of orbitals for hydrogen appears in the end of volume 1, I think in the page of 350 or so. The first time that the orbitals for many electron systems are described and discussed in the second volume, about the middle 550 page, something like this. So this is actually the problem that leads to misconception of the orbital picture. What they means, how they looks like, how to plot them, are they uniquely defined, are they real? Why we so much need them? Why they simplify the explanation of nature? And this is actually the motivation of my talk, is to try to somehow to straighten it out. Of course, in a short time like this, it's impossible to get to details, but at least to give overview picture. So I would like to start with the definition of orbital as one electron wave function, matter wave. So in order to describe it, let's think about hydrogen. So the orbital of hydrogen, x, y, and z, when x, y, and z are the coordinates of the electron with respect to the proton of hydrogen, so 1s of hydrogen is square root of 1 pi, the radius of both to the power of 3, e minus x squared plus y squared plus z squared to the half, divided by the Bohr radius. This is a matter wave. What do we mean by matter wave? It implies that if we will plot the wave function in the Cartesian coordinates, the one electron of hydrogen at any given moment is everywhere. At the same time, the electron is here, and here, and here, and here at the nucleus. So this is a matter wave, which is an abstract concept in quantum mechanics that is not measurable, because only when the experiment is done, is carried out, the experiment makes the matter wave to collapse to a classical particle which is measurable. So the matter wave is something in our imagination that enables us to calculate any measurable quantity from a wave function that describe our system. So if we have hydrogen atoms which don't interact with one another, and all of them are in the ground electronic state, each one of them described by the 1s orbital, which is exact solution of the time-independent Schrödinger equation. And in each one of them, the electron is at the same moment everywhere. But when we do experiments, they collapse. And now depends what the experiment is. The experiment can be absorption spectra. The experiment can be any other type. And any experiment that will be carried out, any measurement that will be done, will be able to predict what will be the results statistically, because the electron is everywhere, just from a single wave function, a matter wave. So the answer to this question here, our method is no. But let me return to this picture and try to describe what are the wave function can provide us, which is measurable quantity. So in order to describe it, let's define the exact one electron density for the 1s orbital of hydrogen. It's the wave function square, which is 1 over pi a 0 to the power of 3 e minus 2 square root x squared plus y squared plus z squared divided by the radius of atoms. Now, we see immediately that the density probability, which is this is the density probability, get the largest value here at the nucleus. So the maximum value is at rho 1sh of hydrogen exact 0, 0, 0. What it means is this is a measurable quantity. Well, this density probability provide the probability density function provide us the information that is needed to calculate the probability to find the electron. And we know from quantum mechanics that rho 1s x, y, and z, in this case is the exact one, dx, dy, dz over all space is equal to 1. And this is exactly what I said before, that the matter waves implies that the electron is all over this space. So this is what it's equal to 1. This quantity, however, provides us the probability to find an electron in the 1s orbital of hydrogen inside a square well, a square cube, I'm sorry, in a cube. And the cube can be here, for example. And the size of the cube is dx. This is dy. I'm sorry, this is dz, and this is dy. So this is the cube. So this quantity tells us what is the probability to find an electron in one orbital of hydrogen in a cube, which is centered in the coordinates x, y, and z. And the cube is delta x, delta y, delta z, which should be as small as we wish. So this quantity goes to 0 as the cube goes to 0. So although the largest probability density to find the electron is at the nucleus, 0, 0, 0, the probability to find the electron there is 0. And it's 0 everywhere. So how we make the plot of this kind of probabilities? Can we measure them? Gedanken experiment. The answer is yes. And the answer is that the picture that you usually have in our mind, that S-type orbitals have a form of a sphere, is correct. But unfortunately, not from exactly the reasons that we think of. It's not true that the electrons are really sitting on a sphere, on the surface of the sphere, because the sphere has 0 thickness. And the probability to find an electron on a sphere which has a 0 width is 0. How to make this Gedanken experiment to find the electron where it is in space? This is out of the scope of this talk. And if you know or you wish to hear the answer to these questions, you have to invite me to give the talk on this subject and to show you how this Gedanken experiment can be done. So I'm not going to discuss it, but the answer is that the probabilities are real quantities. So if we calculate, come to here, are real, in this sense, the answer is yes. But I don't mean that rho exact is really measurable quantity. What I want to say that yes is the probability. The probability to find the electron in space. And the probability is calculated on the base of the calculation of the probability density. So here we are coming to the fact that the orbitals, let's see what I said so far, that the orbitals is for hydrogen atoms, for, as I said here, as any matter waves, is not real. However, the probabilities that are calculated from the orbitals are real. Actually, the fact that by carrying out extremely large experiments which return about the same condition and we measure the same thing, let's assume that we want to measure the location of an electron in the 1s orbital of hydrogen someplace in space. And when we repeat on this experiment over and over, and let's assume that we have got detectors, no errors. The fact that when we repeat on the same experiment over and over and over and over, we don't get the same results, is shocking in a way. Because usually we learn that if we repeat on the same experiment, on the same condition, over and over, and we don't get the same results, it implies that something wrong in our measurement, that our detectors are not good enough. And here we are saying here that regardless of what equipment we have, even if we will have future technology of building detectors with zero error in the measurements, we will not get the same results when we do the experiment over and over and over. Because the electron at the same time is everywhere. This is actually the reason that Einstein was not so happy with quantum mechanics. Probably you have heard his word, what he said, that God doesn't play dice. So he didn't like this statistical approach in basically statistical approach which doesn't depend on errors in the experiment's measurements. The legend, and maybe it was true, that Niels Bohr, in this discussion, answered Einstein, told him, don't tell God what to do. So this is actually show, again, the complexity of the concept of matter waves and orbitals. Now we are coming to this point, to this question. When orbitals provide the exact one electron probability density? When? And the answer is only for one electron systems. So it gives the right answer only for hydrogen, helium plus, lithium plus plus, etc. Since orbitals are the exact matter wave function only for one electron system. And the fact that we can calculate the exact the exact one electron probability density for many electron systems, n is the number of the electrons in the system, many, doesn't mean that the one electron probability density that we get from the calculation of orbitals provide us the exact answer. The fact that all orbitals pictures, the orbital pictures provide us one electron probability density, and the fact that all the one electron probability densities are a single particle wave function doesn't mean that they are equal. As I learned in high school from the Greek philosophers, that is that every goat has a bird, but it doesn't mean that everyone that has a bird is a goat. So you have to be careful about this relationship. So we are coming to the question is how to calculate the exact one electron density, probability density for many electron system. And this is what I would like to start now. So we have the exact wave function, exact solution of the Schrödinger equation for many electron systems. When I is the position of the electron I is equal to 1 up to n, in space with respect to the center of mass of the molecule, or the nucleus in the case of atoms. Now what n is? N is equal to 2 for helium, n equal to 10 for H2O, and n is larger than 1,000 for RNA, just to give you the impression that even many large systems that have electrons can be described by single wave function. Now, what is the one electron exact probability density? Let's put it R of electron 1. It's to take the exact wave function absolute value square, it integrates over the all coordinates except the first one. So this integral implies for all this from minus infinity to plus infinity if the integration is over the Cartesian coordinates x, y, and z. Now, it's interesting to note that if we will do this integration, when we leave out of the integration not the first electron but the second electron, we'll get the same functional behavior. And it will get the same if we integrate all over the electrons from 1 to n minus 1, and we leave out of the integration only the n electron. And the reason is that this wave function change sign by permutation, and all the electrons are exactly the same and are indistinguishable. We cannot distinguish between two electrons. They're identical. And therefore, it doesn't matter over which coordinates we are integrating. And this is why we can write here that this is defined as the one electron probability density, x, y, and z, when x, y, and z stand for the vector position for any one of the electrons. So it doesn't matter which one we take. So this is the definition of the exact one electron probability density for many electron system. So we can put here a V. Now, using this concept exactly, we can repeat on what we said before, and we can say that the probability to find electron in a cube, which is centered in a given point in space for many electron systems, is exactly the same as before. And as before, this quantity goes to 0 as the volume of the cube is going to 0. So it's the same story as we said before for the one electron system. The probability to find the electron at any given point in space is equal to 0. But still, it's possible to carry out measurements. And the fact of life is that we have the ability to do many, many experiments over and over. It doesn't have to be infinite. Eventually, we'll find out in these experiments when the electron is located in, we'll not get the same result when we do this experiment over and over and over. But when we look over all results that we obtained, we'll get statistical picture where the electrons are located. And most of them in the S-type orbitals of an atom will be on a sphere. But you can see that there is probability to find the electron which is located here, to find the electrons also at the moon, in principle, if there are no air and it was vacuum, etc. It's a rare event, but it can be happened. Exactly the same, it may happen rarely, unlikely, that the electron will be at the nucleus. So everything that we say for the one electron system is correct also here. And then we come to the question if this one electron probability density, the exact one, how it's correlated with the orbital picture. So in order to answer this question, we also need to discuss our orbitals for many electron systems uniquely defined. So it's related to this question. So the question, if the orbitals provide something which is related to the exact one electron probability density, is related also to the question how they are defined. So let me start with the fact that in the orbital picture, the orbital's picture is not the exact wave function, as we said here, because in the orbital picture, as I wrote it here, the wave function is written as a separable function. Electron 1 is orbital 1, electron 2 is in electron 2, etc. In this symbol, these orbitals consist of spatial function times spin. I will not write it down, but it implies that in the case of helium atoms, for example, when we have only 2 electrons, one electron phi1 is one s orbital of helium. And the question is how to calculate it, but it's another question. We spin alpha. And the other one is also an orbital of the same one s-type orbital with the spin beta. But there is a problem here that you see as I wrote it, because now you can distinguish between the electrons, not in the case of helium, but in the case of lithium, for example. Because some of the electrons of lithium are in the 1s orbital, one of them is in the 2s orbital. And you cannot distinguish between the orbitals. So what you can do is to define in the orbital picture not the simple product of the one electron functions. Remember, orbitals are one electron functions. So this is orbital, this is orbital, this is orbital, etc. But to use the fact that by permutation of each one of 2 electrons, you get the same wave function, but inverse sign. So the operator that do this job for us is called anti-symmetrization operator. And these anti-symmetrization operators, whenever we change the position of 2 electrons, it changes the sign of the wave function. So if we do one permutation, we change it 1 times. If you do on the top of it another permutation, it will change it again, it will be plus, etc. So this is the picture of the orbitals. And it's possible to show that the rho exact x, y, and z is roughly speaking, the question is when it's true. so let's put it like this, when, is to the sum over all the I occupied orbital which are defined in the orbital picture. So for example, in the case of helium, this will be the Phi1s hydrogen, of helium, x, y, and z, square, 2. Why 2? Because there are 2 electrons. In the case, this is for helium. In the case of lithium, it will be something similar. Plus phi 2s of lithium, like this. So you see that the one electron probability density, the exact one, is approximated. It's not equal to the sum of all the occupied orbitals. So it's, again, not what we had before in the one electron systems. Because now, the exact probability density, one electron probability density, the exact one, is approximated by the sum of all the orbitals. And again, it's repeat on the same thing that I said before, that this by itself is not a measurable quantity. Only the probability that are calculated on the basis of this concept are measurable. So from here, you see immediately that the orbitals provide approximately the one electron probability density. And the question is important, what I wrote here, is when this is true and when it's not. Is it always true? No. Sometimes is terrible approximation. Terrible. Sometimes this is not even approximately describe the exact wave function. I'll give you an example. The example is famous one is fluorine molecule, F2. When you try to describe the exact wave function in the orbital picture of fluorine 2, now it's molecular orbitals, you get out from these calculations that F2 molecule doesn't exist. Namely, the energy of the fluorine molecule using the orbital picture is higher than the energy of 2 separated fluorine atoms. So this cannot be true. And of course, this is an example why the orbital pictures break down completely, even for ground state. So here we are coming to the last part of my talk, where I want to discuss this subject. Are orbitals for many electron systems uniquely defined? And the answer you can guess is no. They are not uniquely defined. So how they can be defined? And what is the difference in the definition? And what is the motivation to use different definitions? So I'll try to sketch briefly the different approaches to describe these orbitals. So there are 3 different ways that I would like to discuss. I move here so you can see. There are Hartree Fock orbitals. There are natural orbitals. And based on DFT, there are cone-sham orbitals. So I'll start on the Korn-Sham orbitals, which are calculated in the DFT calculations. These orbitals has nothing to do with exact wave function. They are used in order to calculate one electron probability densities. And they are very useful, and they are very good, but are not related to the wave function, to matter waves. And this is why I don't want to erase it, but I will put it like this, that I am not going to speak about it. It's out of the scope of the orbital pictures, as we learn in the configurations, electronic configuration in the periodic table, for example. So I would like to discuss about this. What is the difference between these two? Hartree-Fock orbitals are defined on the basis on energy criteria. The nature orbitals on overlapping criteria. And I would like to say shortly and briefly what are these criteria. Using these orbital pictures, we can calculate the ground state energy of our atom or our molecule in the orbital picture, orbital picture, which depends on the definition of all these orbitals. So whenever we define what the orbitals are, we can calculate what is the ground state energy of our system based on the definition of these orbitals. Whatever they are, they will give you an answer. And we can prove that they are larger from the exact value for the ground state. And they are always larger because the exact wave function of our molecules and the atoms are not separable functions. And so therefore, always this will be larger than this. So this doesn't tell me how I can find these orbitals. So let's just try a simple trick using the internet. So how we can find what are the best orbitals to be used to describe what I said before, helium, H2O, RNA, whatever. So using the internet, you can ask people to guess what orbitals are, and then calculate the ground state energy based on the orbital picture. And if you believe that they don't make mistakes, fully mistakes, and they're doing mathematically correct calculations, they'll give you numbers. They tell you the energy of RNA is this and this. And somebody will say the energy of RNA is this and this. It doesn't have to be RNA. If you like simple systems, you can ask them what is the ground state energy of helium. And then you will get many, many results. Which one you need to choose? The one that give you minimum value of this orbital picture. Why? Because even the minimal one is larger than the exact one. So take the minimal one. You want to motivate the people to answer you, give them awards. It depends on you, how much rich you are, and how much you are desperate to get the answer. Now, is this guaranteed that you will get the best orbitals following this criteria? The answer is probably not. It depends how many people will answer you, how clever they are, etc. And then the Hartree-Fock has a solution to this problem. The Hartree-Fock shows that in order to calculate this quantity, instead of solving the time-independent Schrödinger equation for n number of electrons, remember 1,000, more than 1,000 for RNA, which is not possible to solve it even numerically exact. You use this approximation that is written here, and then you end up with, when in this case of 1,000, 1,001 electron differential equations. So for each one of the electrons here, you have one electron Schrödinger equation, effective potential there. And all these functions, all these one electron Schrödinger equations are coupled to one another. And therefore, if you want to calculate the orbital 1, you need to guess what are all the other orbitals. And if you use this guess, you get the orbital 1. Now, if you want to calculate the orbital 2, you need to guess what is orbital 1 and all the others. So you can understand that you have to do this iteratively. First of all, you guess all of this, and then you get 1. Then you use the one that you got and all the others to calculate the orbital 2. And then you repeat on it. And this is why people call it self-consistent field approach. You not do it, the iterations until you get converged results. What is interesting is that when you look at the one electron Schrödinger equation for each one of the orbitals, you see that the approximation that you do is that when you calculate the repulsion, the electronic repulsion of one electron from all the others, you use the approximation that the other electrons, each one of them, is not in a given point in space, but it's in everywhere. So the one electron charge of this electron, when you want to calculate the repulsion of this from electron 1 from 2, the one electron charge of the electron 2 is distributed over all space. And the effective charge is the charge of the electron, which is physical 1, times the density probability of this orbital. And this is what you do. And this is why people call it the mean field. And this approximation can be very good. And sometimes it breaks down completely, as I told you, for fluorine molecule. And this is why people say that Hartree-Fock is a mean field approximation. I will return to this point later, but I want to say that this orbital picture, when it works, it's very good because when you calculate the orbitals, you get also the orbital energies. Each one of these one electron Schrödinger equation give you not only the orbital, but also the orbital energy. And the orbital energy, if you multiply by -1, give you the ionization energy of the atom when electron is taking out from this orbital. And sometimes people measure it, and it's a very good approximation, which works very well. It's called a Koopman theorem. And Koopman, who studied the Hartree-Fock, and this theorem is after his name, moved later to economy and got the Nobel Prize in economy. So it shows that a quantum chemist has a hope to have a large contribution in another subjects as well. And also it shows that, that the mathematics is a language where describes in the same words or the same approaches problems which are very, very different from one to another. So anyhow, this is the Hartree-Fock orbitals based on the energy criteria. What about natural orbitals? natural orbitals are based on the selection of the orbitals such that the exact wave function, the overlap, and this sign is say will give us the overlap, orbital picture. This get the maximum value. So you are looking for the orbitals which describe you the exact wave function in the terms the best in terms of overlapping. Now you may say, how comes? Who cares? If I know the exact wave function, why I should do this at all? Why I should look for the natural orbitals? And other things is how I can calculate this exact many electron system wave function. Again, it's out of the scope of this talk, but these orbital pictures is not only useful when the orbital pictures give you a good estimate for the exact wave function, but even when they are not describing well the exact wave function, they can be used what we call basis functions. So they are using as building blocks. And using these building blocks of the occupied orbitals and the unoccupied orbitals, which people sometimes call it virtual orbitals, if you use all of them as a basis set, you can approximately approach the exact solution, and theoretically you can get it as close as you wish. Of course, numerical difficulties, finite computers, make us not to be able to do it well for many electron systems. But in principle, you can get as close as you wish to the exact wave function. Now, this orbital picture, which called natural orbitals, has the power that it helps us to understand the chemistry of the system extremely well, or better than the Hartree-Fock orbitals. They give us insight to the molecular structures and sometimes about the dynamics of the reactions. And this is why people use the natural orbitals as a tool for analyzing the molecular structure and dynamics, etc. So we see they are not uniquely defined, but it seems to me that I cannot finish my talk without mentioning something else that come to be more and more, I cannot say popular, but more relevant to different kind of experiment that people are doing. And by this, I will finish my talk. So I want to describe another type of orbitals. And for this, I need to erase, maybe I'll erase this. The Dyson orbitals. So psi R1, R2, up to Rn is a n particle, n electronic wave function. When R1 up to Rn, as before, stands for the position of the electrons with the spin. Now, here we are assuming, and we put a question mark, that we can describe the unseparable function of n particles as a product of ionic wave function of n minus 1 particles, electrons, times a function of the last electron. You can see that here in this presentation, we have much more electronic correlation than we had before. Because this is not an orbital. Orbital, as we said, it's one electron wave function. So this is an orbital. These are not orbitals. Before, when we discussed the Hartree-Fock approximation or the natural expansion analysis, orbitals, in these approximations, every one of the electron occupies one electron wave function, orbital. But in this case, n-1 electrons, they have the full electronic correlation among themselves, while the other electron move in a field of the average field of all the others. So this is approximation of separability, which is less separability than before. Now, of course, these electrons are not distinguishable. We cannot distinguish between one electron to the other one. Therefore, we have to put here the antisymmetrization operators, as we said before, which implies that we have all possible permutation between this electron and this electron. So this electron not necessarily occupy the n electron, it occupies all possible electrons, but it's one electron wave function. So this is an orbital. Before saying what is the Dyson orbital, let's say that for any pre-selected wave function like this, we can say that phi Rn, and then with the permutation, electron permutation, we have all the other possibilities, is simply the overlap between this wave function ionic one and the exact wave function, when here we integrate over the all n-1 electron. So by this symbol, we imply that we take this wave function, complex conjugate, multiply by this wave function, and integrate over the position of the electron 1, 2, up to n-1. And therefore, we end up with a wave function of one orbital. And the question is if this orbital is normalized. This pre-selected ionic orbital is normalized to unity. But when we do this, I can tell you that it's possible to say that this one is smaller or equal to 1, and the equality to 1 is if and only if this is exactly this is 1. So if the exact wave function is separable, then it's 1. But since we know that the exact wave functions that we are talking about, atomic and molecular electronic states, are not separable, we can remove this equality. So always the overlap will be smaller to 1. And as this overlap becomes closer and closer to unity, it implies that this approximation is better. The question, what is the best product of functions that we should select such that this overlap will be as much as closer to 1, is not the issue when we discuss the Dyson orbital. In the Dyson orbital, the selection of the ionic one is based on physical grounds. For example, if somebody look and study for the highly excited states of atoms and molecules, then it's reasonable to think that the one of the electron which is excited, doesn't matter which one, of course, it's far in, statistically, it's far enough from all the others, such we can think about it that all the other electrons are inside some sphere, while the additional electron is far apart. In such a case, you can use classical arguments and say that actually all the others, particles, charged particles, the nuclei, positive and the negative electrons, are in the center of the sphere, and therefore it looks like hydrogenic-like orbital. But this is not exactly so, of course, because we know it's quantum mechanics that, as we said, in the case of wave functions and orbitals, that at the same moment the electron is everywhere. So this is why we have to be careful with this description. But we can say that we assume that it's not so bad approximation to think that this ionic wave function is the ground state energy of the n-1 electron system. So this is how we pre-selected these states. And what is coming here is the Dyson orbital. So the Dyson orbital is not normalized to unity, and it's obtained on the ground of our assumption that we can write this, describe the n electron wave function approximately in this way. Well, what are the situations that this approximation is very helpful? As I said, in the cases when we have highly excitations of one of the electrons. But I will give you, and this is something which looks to me very special, that in recent experiments that were carried out in Ottawa by Kokum, they study the multiphoton dynamics when the system interacts with strong laser field. Now you take a molecule or an atom in the ground electronic state, shine on it strong lasers, and the electrons absorb many number of photons. And one of the electrons, it doesn't matter which one, absorb many photons and get to a very highly excited state. And there are two options. One option that it's ionized, and the other one is that there is a competitive situation that the electron is relaxed to the ground and release all the extra energy that he absorbed as high photon and energy photons, as high energy photons. Now, in this description, in their measurements, they claim that they were able to get tomography imaging of the Dyson orbitals. Is it really the Dyson orbitals is not so sure, but one for sure is that they can think about it, that the whole photon-induced dynamics is associated with a single orbital wave function. And they assume that it's associated with this ionic one. And the result that they obtained enabled them to get, actually, by convolution procedure, to find out what is the one electron probability density which is associated with the Dyson orbital. So the Dyson orbital itself is not a measurable quantity, as we discussed, because it's a wave function. As we discussed before during this talk, that the one electron probability densities are associated with measurable quantities. And in this case, the idea is that one electron probability density, which is the Dyson orbital, is associated with a measurable quantity. So here we are coming to the end of my talk. Think how nice it is that the all properties of the atoms in the periodic tables, or most of them, let's put it this way, we can describe by using the electronic configuration. In this case, is the Hart-Rifok orbitals. This is my interpretation. So we use approximated description of the exact wave function, orbital pictures, configuration, and then chemists know very well how useful it is. Look at their papers. So this is what I want to say in the end of my talk, is to say orbital pictures is very useful. But the wisdom is to use it when they give you the right answer. Well, thank you.